This question asks us to find the current for time greater than 0, and it's a current that's flowing through this corner in the upper left. First question we need to ask ourselves is it a switched DC first order circuit? It's definitely switched. It's switched to time equals 0. You can see the switch here that switches to time equals 0. And it is a first order circuit. There's only one energy storage element, and it's right here, that capacitor. So we can use our theory that we've developed so far. And we know that in that theory, the first thing we'll find is, even though it asks us to find the current, we are going to find the voltage across that capacitor. So we'll need to begin by defining what that voltage is. Since we're defining our current going into the top, it's most natural to define our voltage across the capacitor in this method, with the current going in the more positive, exiting the more negative, because with that definition we can say I equals C dV dt. All right, so let's begin. The first step is to draw the circuit for time less than 0 in order to determine our initial conditions, which is V sub C at t equals 0 plus right after the switch, which of course has to be the same as the voltage across the capacitor just before the switch was thrown, because the voltages across capacitors can't change instantaneously. And by drawing at t less than 0, we know we're in DC steady state, so that capacitor looks like an open. In general, when we draw it in DC steady state, there should be no capacitors, they should be open. There should be no inductors, they should be closed. And there should be no switches or U of T's, those should be evaluated. Since our switch opens at time equals 0, it must have been closed for time less than 0. And again, realize that even though we are asked to find I, I'm not drawing it here because our first goal is to find V sub C. Now I've got these two resistors and they're clearly in series, so rather than draw each one separately, I'm going to simplify what I can. And what lets me simplify them is, well, firstly, they are in series. All the current that goes through this one must go through this one, so they're definitely in series. And secondly, I can simplify them because they are far away from my V sub C over here. So by combining them, I'm not destroying anything that I need to find. If I needed to find for some reason the voltage across this 3 ohm resistor, I would not be able to combine them because I'd be destroying that voltage. Okay, so we've got this 3 amp source, and when I analyze these things, the first thing that I think of is, how is the current flowing? And I can see the current flowing through a loop here, and I can see it flowing through a loop here, and I can see it cannot flow through this loop. Since there's no current flowing through that loop, does that mean VC is 0? Absolutely not. You can have voltages without currents. Just a plain old 9-volt battery held in your hand has a voltage across the terminals, but no current. What it means is that since there's no current flowing through that 4 ohm resistor, I know right now that the voltage across that 4 ohm resistor is 0 volts. So VC therefore has to be the same as that voltage. And that simplifies my circuit a lot. In fact, I'm going to redraw this circuit one more time. I can combine these two resistors. Now you might say there's no way to combine them since I want to find the voltage across this 2 ohms resistor, and by combining them I'll destroy that. But I'm really not. Watch what I do. In 2 steps, if I firstly just move my resistors to one side of that current source, I get this, 4 and 3. And I think it's pretty clear that that does not change what VC is at all. I haven't changed my nodes at all. I have 3 current carrying nodes over here, and I have the same 3 current carrying nodes over here. So if my nodes haven't changed, my voltages haven't changed at all either. And you can see that combining these two does not change my voltage, because I could redefine where I pick off that voltage between here. And clearly now I can combine these resistors and they haven't changed where my nodes are. Now, although all this is true on a, I'm just justifying, now although all this is true, I'm just justifying what I've done. On a test or when doing your homework, just simply look at this schematic and simplify it down to this. 2 VC, and this 2 is in parallel with the 4, and we've got our 3 ohm over here, our 3 amp source. So by inspection, VC is going to be equal to the current through that resistance times what that resistance is, and that resistance 2 in parallel with 4 is product over sums. So we can simplify here that 3 goes into 3 once, 3 goes into 6 twice. That gives us 8 over 2 or 4 volts. So that's our initial condition. Next, we'll draw it for time greater than 0. And in this region, we want to find tau. In order to find tau for an RC circuit, it's equal to the resistance that the capacitor sees times whatever that capacitance is. So let's redraw what our circuit is. For time greater than 0, here's our capacitor. We have our 4 ohm here. Now the switch is opened, and since the switch is opened, no current can flow through that 2 ohm resistor. So I can just simply not draw that whole system and not change the circuit at all. We have our 3 amp here. We've got our 4 ohm over here. And the question again is, what resistance does the capacitor see? What resistance does this guy see? How hard is it to push current in here and to suck it out at this end? When we want to measure the equivalent resistance of sources, the source resistance of a voltage source is 0, and the resistance of a current source is infinite. So from the perspective of the capacitor, we have a 4 ohm, we have a open, current sources go to opens, voltage sources go to close. We have 4, and this is what the capacitor sees, is that 4 in series with a 4, so therefore Req equals 8, and tau equals our capacitance 1 farad times 8 equals 8 seconds. And that's step 2. Next, step 3. Find what the circuit looks like at time equals infinity. We're back to DC steady state. There's no current moving. And our goal here is to find what our VC at infinity is. So since we're at DC steady state, our capacitor looks open. The voltage across it is what we're trying to find. We have a 4 ohm resistor here, but we don't really even need to draw it since we know there's no current going through, so it doesn't affect the rest of the circuit. We don't have to draw our switch since it's open. We have a 3 amp source here that's still pumping out juice, and our 4 ohm resistor over here. So again, you can analyze this using a lot of different methods, but I prefer intuition, and all the basis of intuition starts off by saying, where does current flow? It flows around that rightmost loop. And with 3 amps flowing through a 4 ohm resistor, there must be 12 volts of voltage pressure across that 4 ohms. And if there's 12 volts there, there's got to be 12 volts between these 2 points since it's connected by a wire. And since we know that there is 0 volts across the 4 ohms, since there's no current flowing through it, that means there also has to be 12 volts between these 2 sides. So just by inspection, we can see V of infinity is equal to 12 volts. Sometimes you might see me put little lines on top and bottom of the voltage symbols like I did here. That just emphasizes that it's a capital V and not a small case v. We use capital letters for things that are DC that don't change in time, and lowercase letters for things that do change in time. All right, now we can do our 4th step, which is just to plug it in that equation. Vc is equal to V of infinity plus V0 minus V of infinity times e to the minus t over tau. So plugging in our numbers, that gives us 12 plus 4 minus 12, which is minus 8, e to the minus t over 8. Okay. We're getting close. Don't forget that that unit is in volts, and that's not what we were asked to find. So our last problem, last section, is how do we convert that I to a current? And we have to look at time greater than or equal to 0 for that. A lot of different ways. There's smart ways and there's not so smart ways. Don't think that this voltage across the capacitor has to be the same as the voltage across the resistor so you can use Ohm's law. It's a completely different voltage across the resistor. The only thing that's the same is the current. But in this example, we can use the relationship I equals C dV dt, that basic relationship of a capacitor, to find out what our I is. Here it's equal to our capacitance, which is just 1, times the derivative of this. The derivative of a constant like 12 is 0. The derivative of minus 8 e to the minus t over 8 would be minus 8 times 1 over minus 8 e to the minus t over 8. And all of a sudden we're talking about amps. And so this would just simply be e to the minus t over 8 amps. And that's true for time greater than 0. And that answers the question. Since we've got just a little space left, I'm going to ask a couple of other questions. What would happen if instead we were asked to find the voltage across this 4 ohm resistor? How would you do that? I'll call that V sub R, or V sub 4. You might be tempted, and you'd be almost right, to say V sub 4 is just Ohm's law. We just found out what I is here, so therefore it has to be equal to I times 4. And that would be almost correct, except realize that the formula for Ohm's law assumes a polarity. It assumes that current is defined entering the more positive and leaving the more negative. But up here, we've defined the I as entering the more negative and leaving the more positive. And since that's opposite of the way we defined it in the upper left, we have to add a minus sign to correct for it. What would happen if instead we were asked to find the current I for all time? We'd look back to our drawing for time less than 0, and we'd observe that there was no current flowing through the capacitor for time less than 0. And so we would modify our current for all time to be equal to 0 for time less than 0, or what we just determined it to be for time greater than or equal to 0. Notice this, that the current suddenly jumps. It jumps from 0 to 1 instantaneously at time equals 0. There's no rule for capacitors that says that the current has to be continuous. The rule for capacitors is that the voltage across it is continuous, just like the rule for inductors is that the current through an inductor is continuous. But a voltage across an inductor, current through a capacitor, or current through and voltage across a resistor can all instantaneously jump at t equals 0. So I guess I should be very precise about where I place this equals. If it was equals at 0 or equals right after 0, and that's a question the mathematicians can care about, but for electrical engineers you'll get full credit either way, since there's no change in the energy dissipation of the circuit between those two options. Since there's no measurable difference between those two outcomes, we don't care.